Welcome to tutorial 7. Today we're going to discuss about Taylor polynomial. So here we're given a task which says find the Taylor polynomial of degree 4 for the function given to us, which is x to the power minus 2 about the point x0 is equal to 1. And then we have to use the results that we get in part A to approximate the function at 0.9 and 1.1. And then we'll use the Taylor remainder to find an error formula for the Taylor polynomial and give error bounds for each of the two approximations that we made in part B. And then we'll have to see which of these two approximations is closer to the correct value. So here I have first shown you what Taylor theorem is. Let's discuss it a little bit. So here we have let f be an n+1 times differentiable function on an open interval containing the points a and x. Then f of x is equal to f of a plus f or first derivative of the function at a times x minus a plus second derivative of the function at a divided by 2 factorial times x minus a squared, plus we have until the end, which is the nth derivative of the function at a divided by n factorial times x minus a to the power n. And then at the end, we add the error, so the Rn of x. So the error here, or the formula for error is shown here. So what is this one here? The first formula, that's the formula for Taylor polynomial. And this one here is the formula for the error in estimating or approximating the function. So here we have just the very next term. So here the last term here is until the nth term, and the error will be the very next term, which is the n+1th term. So it's the derivative of f to the power n+1 of the function at the point c, and c here is between a and x, some point between a and x, where this function here gives the maximum. So, or where the derivative at n+1th term gives the maximum. And then we have divided by n+1 factorial times x minus a to the power n+1. Okay, so let's go ahead and get started on working for the task. At first, I will write down for finding out to the degree 4, that's what the question says, find the Taylor polynomial of degree 4 for the function. So let's write how the formula will look like for until degree 4 for the function of the Taylor polynomial. So I could write it f of x, or I could also write it as Taylor polynomial. It's up to you, or even I like to write it as, maybe I'll go for that. That's polynomial degree 4 x. So the Taylor polynomial of degree 4. Now here for this one, the formula will look like this. So f of x0 plus f dash x0, okay, times x minus x0 plus second derivative of the function divided by 2 factorial times x minus x0 squared, plus we have the third derivative of the function at x divided by 3 factorial times x minus x0 to the power 3, plus, since we have to do for degree 4, so we'll go until the fourth derivative of the function divided by 4 factorial x minus x0 to the power 4. That's what the formula will look like. Now Let's go ahead and find out all the derivative of the function and their values at x0, because we need to find out the derivative of the function at first derivative, second derivative, third derivative, fourth derivative at x0. So here, yeah, I didn't write that part, I guess, so properly. So here it will be all x0s. Okay, so let's go ahead and write down our function. Here is x to the power minus 2, and putting in the value of x0 here, which is, as we saw in the question, the value of x0 is 1. So f of 1 will be 1 to the power minus 2, which is equal to 1. So now for the first derivative of x, we have here minus 2 times x to the power minus 3, and putting in the value of 1 in the first derivative will give us here minus 2 times 1 to the power minus 3. 1 to the power anything is 1 times minus 2 will give us minus 2 here. And then let's go ahead and find out the second derivative of the function now. So minus 2 times minus 3 is plus 6 here, times x to the power minus 3 minus 1, which is minus 4. And putting in the value of 1 in the second derivative will give us here now 6 times 1 to the power minus 4. So as you know, 1 to the power anything is 1 times 6 is 6 here. Now, the third derivative of the function is minus 24 x to the power minus 5. And bring in the value of 1 here will be minus 24 times 1 to the power minus 5. So again, it will be minus 24. The fourth derivative now. So you don't write 4 derivatives with all the lines. You just write it as a number here. So fourth derivative of the function will be minus 24 times minus 5, which is 120 x to the power minus 6 here. And putting in the value of 1 here will give us 120 times 1 to the power minus 6, which is equal to 120. Alright, so we got all the values that we need to put in our function to get the polynomial here. So let's write on the other page. So our polynomial now will be, maybe let me just replace the value of x0 with 1 and make it look more clear to you. So here we'll have f of 1 plus f dash of 1 divided, no, it doesn't divide here, so I'll just write it a bit here. So we have f dash of 1 times x minus, so we have x minus x0 here, which is, as we know, x0 is 1. So we'll replace it here. Plus we have the second derivative of the function at 1 divided by 2 factorial times x minus 1 squared, plus the third derivative of the function at 1 divided by 3 factorial times x to the power, x minus 1 to the power cube. And then we have here plus the fourth derivative of the function at 1 divided by 4 factorial times x minus 1 to the power 4. Okay, now that's more simplified. And now f of 1, we'll just take in our values. So f of 1 is 1 here. Plus we have f dash of 1 the value is minus 2. So that's minus 2, and here we have a plus, so it will change the sign here. Then I'll just replace it with minus 2 times x minus 1 here. Plus we have, if second derivative of 1, the value is 6. So we have 6 divided by 2 factorial. So 2 factorial is 2 times x minus 1 squared, plus, if third derivative, the value we have got is minus 24. So again, it has to be minus here. 24 divided by 3 factorial. 3 factorial is 6 times x minus 1 cubed. Then we have plus fourth derivative, where we have 120 divided by 4 factorial. That's 24 times x minus 1 to the power 4. Okay, now to make it more simplified, we could cancel here 2 1s are 2, 3s are 6 1s are 6, 4s are, and 24 1s are 24 5s are is 120. So now let's write it again. It's 1 minus 2 times x minus 1 plus 3 times x minus 1 squared minus 4 times x minus 1 cubed plus 5 times x minus 1 to the power 4. Okay, so we have got our polynomial. That's, I think, the first part here. So find the Taylor polynomial of degree 4 for the function about the point x0 is equal to 1. So we just found out the Taylor polynomial for the function of degree 4 here. So that's, we are done with the first part. Now let's go ahead and see how to work out the second part. We'll use this result in part A and approximate the function at 0.9 and 1.1. So here now, f of 0.9, maybe I'll use different color. So here, f of 0.9 now. So we're using exactly this formula above here, right? So we have 1 minus 2 times, x is now replaced with 0.9. So we have 0.9 minus 1 plus 3 times 0.9 minus 1 squared minus 4 times 0.9 minus 1 cubed plus 5 times 0.9 minus 1 to the power 4. Now that, if you work it out with your calculator, maybe you get the value here as 1.2345. Okay, so what we're solving here is now part B, and let's go ahead and solve now for the next one, which is f of 1.1. So here we have f of 1.1, which is equal to 1 minus 2 times 1.1 minus 1, plus we have 3 times 1.1 minus 1 squared minus 4 times 1.1 minus 1 cubed, plus we have 5 times 1.1 minus 1 to the power 4. So that gives us the value here as 0.8265. So those are the approximations for the function at 0.9 and at 1.1. Now we'll go ahead and do the task or the part 3, which is use the Taylor remainder to find an error formula for the Taylor polynomial. So what we're first supposed to do is find an error formula. So since we have seen in the first slide that the error formula is, or the remainder formula is, for the remainder at n, we have the derivative of the function nth plus 1 derivative of the function at c divided by n plus 1 factorial times x minus a, or here you can just say as x0, because for us a we have seen in the quotient as x0. So at times in the quotient it could be mentioned as an x0 or an a, don't get confused. So here we have x minus x0 to the power n minus or plus 1. Okay, so that's the general formula. Now our formula would be here, because we have found until the fourth derivative of degree 4. So this one will be the next term, which is the fifth one. So the remainder term at, sorry, not x is not 5. Skip it as an x over here till now. And here we have the fifth derivative of the function at c divided by the fifth factorial, so times x minus x0, which is 1, to the power n plus 1, that's 5. So that's our formula that we need to find the error of this Taylor polynomial in our question, right? And also we need to know that these are absolute values. These are absolute values. The error is an absolute value. Okay. Now, in part C, after we have got the error formula, what it says is give error bounds for each of the two approximations made in part B. So we need to now get to the error bounds. So the error bound for approximating the function at 0.9. So we'll have to use this formula above here. But before that, we need to find out the value of c here. So what will be c? C will have to be a value. So let me work it out in a different color. C will have to be a value where the fifth derivative of the function here should be the greatest. So first of all, before that, c is a value which is between a and x. So c is between a and x. So here our a in the question was represented as x0. So our c is between x0 and x, and we know that x0 is equal to 1 for us, and x is this value here. So x is equal to 0.9. So c is between 1 and 0.9 here. And so you can say c is greater than 0.9 and less than 1. Now, for which of these two values, that is 0.9 and 1, the fifth derivative of the function here has the greatest value? So we have to find out the fifth derivative of the function at 0.9, and we have to find out the fifth derivative of the function at 1. And that will say us at which place it is the greatest, and we'll take that value for c. So I'll just go back here and find out the fifth derivative of the function, and that will be 120 times minus 6, which is minus 720 times x to the power minus 7. So we have minus 720 times x to the power minus 7. And so here it will be minus 720 times x, which is 0.9 to the power minus 7. And that is equal to minus 1505.34. And we have to take the absolute value for this one here. So as you know, that's just 1505. And here, if you calculate this one here, we'll have minus 720 times 1 to the power minus 7. So 1 to the power minus 7 is 1 times minus 720 is minus 720. But the absolute value of that would be 720. So which one is larger? As you can see, this value is larger here. So which means that for C, we'll take the value of x as 0.9. So here our C, you can say therefore C is equal to 0.9 because that's where the fifth derivative of the function is largest. So yeah, we've got the value for C. Now we'll put that in our remainder formula and get the error bound for the approximation here. So here our remainder term is equal to the fifth derivative of the function, which is minus 720 at C. So here we have fifth derivative of the function divided by 5 factorial times we have x. Now we know a value of x is 0.9 minus 1 to the power 5, and we have to take the absolute value of this. So this here is, so the remainder or the error should be less than equal to minus 720. I'm replacing the C now with 0.9 here to the power minus 7 divided by 5 factorial times 0.9 minus 1 to the power 5, and that is equal to 1.254450949 times 10 to the power minus 4. So that's the error bound for approximating the function at 0.9. Now we'll go ahead and find out the error bound for approximating the function at 1.1. So here we have to find out now the error bound for approximating the function at 1.1. So again, we need to work out our value for C. So C is between, maybe I'll use again a different color here, easier to understand. C is between x0 and x. So our x0 is 1 and x is equal to 1.1. So C will be greater than 1 and less than 1.1. And now putting them in the fifth derivative of the function, which is minus 720 times 1 to the power minus 7. And here we have minus 720 times 1.1 to the power minus 7. So this one here is equal to minus 720, and this here is equal to minus 369.47. So the absolute value is 720 here, and the absolute value is 369.47. So as we can see over here, this is larger than this 720 is larger than 369. Therefore, for C, we'll take the value as 1, as we want to take the value for C for which the fifth derivative of the function is the largest. So we'll take for C, so you can say therefore C is equal to 1 here. And now to find out the error, we have the fifth derivative of the function at C, which is 1, divided by 5 factorial times x value, which is 1.1 minus 1 here to the power 5. And of course, we'll take the absolute value of that. So here we have minus 720 times x, C, sorry. So that's 1 to the power minus 7 divided by 5 factorial times 1.1 minus 1, that's 0.1 to the power 5. And that gives us the value here as minus 6 times 10 to the power minus 5. So that is same as saying 6 times, absolute value of that would be 6 times 10 to the power minus 5. Okay, now we have to see our third part of the question, that is in part C, the third part of the question. So which is, which of the two approximations in part B do you expect to be closer to the correct value? So we just have two approximations done. So we did two approximations, that is f of 0.9 and f of 1.1, and we got two values here. Which of them is closer to the correct value? We can find this out by looking at the error. Whichever is having lower error, of course, that's more closer to the correct value. And we just found out their error bound. So here we have found out the error bound for the function at 0.9. So that's kind of, you can say 0.000000125 here. And here we have the error bound for the function at 1.1, which is 0.406. So the lower is here. So this one here is having lower error than the previous one. Therefore, this here, the function at 1.1 is more closer to the correct value than the function at 0.9. And that's the end of this section.